All right, good morning, everybody. So just to remind you where we are in the lectures. We've implemented two different kinds of stacks so far. So we've implemented a list-based stack and an array-based stack. And now we're going to, in today's lecture, we're going to implement a third kind of stack, this time using a linked sequence of nodes. Now, we've got three different implementations of a stack, but they all work the same way. So they all have the same methods. They all represent the same sort of idea, right? They all represent a stack of stuff. So at this point in time, we can make them almost interchangeable if we introduce an interface for the stacks. Right? So we can make an interface called stack. Right? So notice it's marked as an interface and not a class. Right? And now we can declare all the methods that stacks should provide. So we can say that every stack has a size method. Every stack has an isEmpty method. I'll come back to this one in just a moment. Right? Every stack has a push method, and every stack has a pop method. Right? And so by creating an interface for all of our stacks, right, we've got a common way for people to use our stack classes. Right? In other words, people can choose which kind of stack they want to use, right? And they can use it according to the interface, according to the stack interface, right? If later on they decide, hey, they picked the wrong stack, right? All they have to do is change their type of stack that they used, and as long as they use the interface for their code, none of their other code has to change. And I'll explain what that means in a few minutes. All right, so we haven't seen this yet. So remember, in an interface, methods generally do not have an implementation, right? So the size method here doesn't say how a stack figures out how many elements are in the stack, right? But we've got this isEmpty method here, which looks a little bit different, right? It does have a body right there, right? So it has an implementation, right? And it's also marked as being a default method. Right? So we haven't seen these yet in this course. So an interface is allowed to have default methods, right? Classes cannot have default methods, right? So default methods exist only in interfaces. Your interface does not have to have any default methods, right? So a default method in an interface is simply a method that has an implementation, but there are some restrictions on how you implement the method, right? So remember, we're in an interface, right? Interfaces have no fields. So we have no idea how any particular stack is being implemented in the interface. Right? So your default method implementation, right, isn't able to access the field of any particular stack in its implementation. Right? So what can it do then in its implementation? Right? So here we see that we're using the size method. Right? And the size method is a method that's in the interface. So this is allowed. Right? We know that every stack has a size method. Right? Therefore, calling this.size will always work, right? Even though we don't know how it's implemented, it's guaranteed to work, right? Because it's a method that's in the interface, so that's allowed. Right? So a default method, the implementation can only use methods from the interface itself. Right? Now remember, there's something else that's peculiar to Java, right? Every object in Java is an instance of big O object. So you're allowed to use any of the methods that are found in java.lang.object. Right? So if your default method needs to use equals, that's fine. Right? We know that equals must exist for every object in Java. You can go ahead and use equals in your default interface method. Right? And finally, if your interface is what's called a sub-interface of another interface, you are allowed to use the methods in the super interface. Right? So we haven't talked about this yet in the course. But you might remember back to when I told you about lists. And we saw that the list interface was actually a sub-interface of this thing called collection. Right? And so inside the list interface, if you had a default method, you could use one of the methods from collection, right? Because every list is also a collection. All right, so you might wonder why these things exist in the language. And it turns out they did not exist in the language until Java version 8. And so one of the problems that you run into with interfaces if you create an interface that is widely used, so many other people use your interface, you're kind of stuck with it, right? It's impractical to change the interface because changing the interface will force everybody that's using the interface to now change their code, right? So for example, if you decide you have to add another method to your interface, now everybody who used your interface now has to add that method if they want to use your updated interface. Similarly, if you try to take away a method from the interface, everybody who implemented your interface now has to go into their code and take away that method that no longer exists if they want to use your updated interface. Creating an interface more or less creates permanent code. Right? And this is a problem when you are a language implementer like you are if you're creating the Java language. Right? So Java had all of these existing interfaces, and then in version 8 of the language, a very large update was added to the language. So there's these things called Lambda expressions, which are not a topic in this course. But it turns out to add Lambda expressions to the language designers had to change many, many existing interfaces. And they decided that rather than break everybody else's code, right, we would add default methods to the language, right? So that way the language designers, they can change their interface by adding default methods to their interface, right? And that gives everybody who previously used their interface, right, they now have an implementation of that default method, They don't have to go and re-implement it on their own in their classes that implement your interface. Right. Okay, so that's just a little bit of a side there. Let's go back to the our stack interface. So now that we've finally got our stack interface, we can go ahead and update our list-based stack so that it implements the interface. And it's dead easy to do, right? So before, our class was just called listStack, right? And it uses an array list to hold the stack of strings, right? If you wanted to implement the interface, all you have to do is write implements stack, right? It provides, our listStack class already provides a size method, right? And that size method matches the signature of this size method in the interface, right? We get for free the isEmpty method, right? That's part of the interface, so we get that one for free. Right? The interface says that push and pop must exist, right? And push and pop already exist in our listStack class. So we're done. There's almost nothing to change. So having your class implement an interface is generally very easy to do. Right? All you do is you say it implements the interface and then make sure every method that's in the interface also shows up in your class, right? And away you go. Now, in the previous lecture, we implemented a stack using an array, but it was an array of int. So I can't make that class implement the stack interface, right? Our stack interface is strictly an interface for a stack of strings, right? So we'll have to try to fix that one later on. Sorry, here it is, right? We can't do the same thing for our array-based stack of int, right? Because our interface is strictly designed for strings or stack of strings, right? And so we're going to fix this in a little bit when we learn about implementing what are called generic classes. Okay. So now we want to implement a stack in yet a third way. So here we're going to implement it with what's called a linked sequence of nodes. The reason we want to do this is because if you look at the list and array-based stacks, right, and if you look at their two fundamental operations, right, there's pop and push, right, you can see that pop, its worst case complexity is always in O1. Right? In both the list and the array-based implementations, all you're doing is adjusting where is the end of the stack. Right? So there's only a little bit of bookkeeping to take care of, and all of that can be done in constant time. The problem occurs with push. Right? And so in both the list and array list-based implementations, when you push an element onto a stack, most of the time the operation is in O1. However, when you run out of space in the array, or if you run out of space in the underlying array list, then you have to resize the array, right? And that operation takes big O of n time, right? So the worst case complexity for push is in big O of n, which may not be acceptable for your particular application, right? You might be in a situation where you need your methods to be very fast, right? And you want to guarantee O1 complexity in your push operation. So the question is can you actually do this? And the answer is yes, you can, right? But you have to pick a different implementation of your stack. Okay, so how are we going to do this? So we're going to do this by creating what's called a linked sequence of nodes, right? And so many data structures that represent a collection of some kind can be implemented using a node-based approach. So in this course, we're going to implement stacks using a linked sequence of nodes, right? We're also going to hopefully get to linked lists. In some of your discrete math courses, you may have seen trees and graphs, right? And you might have been told that those are collections of nodes, right? You'll also see trees and graphs in SIS 235. So those are other examples of data structures that are typically implemented using nodes, right? Graphs show up all over the place. So the 365 is your algorithms course, and there's a course in the math department that is nothing but graph theory, right? So that's Math 401 if you're interested in taking that course. Right? So what's a node? So a node stores some information, right? So in our case, we want a collection of stuff, so it's going to store an element of some kind, right? More precisely, we're going to store a reference to an element, right? But the node also stores some other pieces of information. So a node is going to store references to 0 or more other nodes. Right? And so these nodes are often called links. Right? So for a stack is just a linear collection of elements, right? There's the top element, right? That's connected to the next element, right? Which is connected to the next element, which is connected to the next element, and so on and so on and so forth. Right? So your elements are arranged in a linear sequence starting from the top element. Right? And each element is connected to the next element deeper in the stack. Right? So a node for a stack then can store the element or a reference to the element. Right? And then it's going to store a reference to the next node deeper in the stack. Right? And that node is also going to have a reference to an element, right? And a link to the next node deeper in the stack, and so on and so on and so forth. Right? So here's a picture of a node. So that's a picture of a stack of size 1. Right? Here's our picture of a node. So this is going to be for a stack of strings. Right? So the node holds a reference to a string. Right? And I'm not showing it as a reference here. I'm showing it as an actual string. But you have to remember that in Java, this is going to be a reference to a string. Right? So this node holds a reference to the string A. Right? It's the only node in the stack, so there is no next node in the sequence. So to indicate that there is no next node, we're going to use null to represent to indicate that there is no next node. Right? Null meaning no object. Right? So our top of the stack refers to one node, right? And there is no other node in the stack. Right? So the thing shown in red is our element, or reference to an element. Right? And the arrow, and the null in this case, is our link. Okay, so suppose I want to add another element to the top of the stack. Right? So what do? Well, all of our elements are stored in nodes, so I need to make a new node. Right? So there's my new node. Right? So it's going to hold a reference to the string B. Okay, so I want to link our nodes together. Right? So I want B to indicate that the next node in the sequence is the A. Right? So we're going to set the link of the new node to point to the current top node. Right? Okay, so now that we've got a new node on the stack, or sorry, another element on the stack, we're going to adjust this thing top so that it now points to or refers to the new node that we just created. And if we're keeping track of the size of the stack, we're going to add 1 to the size of the stack to indicate that there's a new node, a new element in the stack. Right? So that's a stack of size 2. Right? So if you repeat the process to get a stack of size 3, right, so make a node, set the element in the node, set the link so that it points to the current top, and then adjust top so that it points to the new node, right, we end up with the following picture here. All right, so how do you pop an element off the stack? So to pop an element off the stack, we need to return the element that's sitting in the top node. Right? So we need to remember that there's a C sitting in the current top node. Right? So we're just going to obtain a reference to the element stored in the current top node. Right? So we're going to remember that C. Right? We're now going to make top point to the next node in the sequence. Right? Now the question is how do you get to the next node in the sequence? Right? Well, top is pointing at this node here. Right? This node here is linked to the next node in the sequence. So if you follow that link, right, you get to the next node in the sequence. Whoops, sorry. There we go. Right. So we're going to adjust top so that it points at the second node in the sequence. Right. The top node is going to go away. Right. We don't have to do anything special in Java to make it go away. It's just going to go away. It's going to go away on its own. Right. We've removed one element from the stack, so we're going to decrease the stack size by 1. Right. Now don't forget we have to return that element that was sitting in the top node back to the caller, right? Which is why we remembered it in step 1. So now I'm going to return the reference obtained in step 1 back to the caller so that the caller knows what the popped element was. Right. Okay. So what does a node actually look like? So how are we going to implement this node class? Right? So every node, right, has an element, right? In this case, it's going to be a string, right? So a node is going to be an aggregation of one string, that is the element. Right? Every node has a link to the next node in the sequence, right? And so the way you show that is with the solid line connecting node to itself, right? So this says that node is an association of one other node, right? Which means that every node is going to have a reference, right? That is also a node. All right, so what does it look like? So let's go and jump into Eclipse and see what this class is going to look like. So I'm going to make this class called linked stack. Right, so this is a stack of strings using linked nodes for its representation. We're going to implement the stack interface. Right, so we're going to have a size method, an isEmpty method, a push and a pop method. For convenience, I'm going to keep track of how many elements are in the stack. So size is the number of elements that are going to be in our stack. It turns out you don't have to keep this, you don't need this field, but it's convenient if you have it. Right? What else is going to be part of our stack? Well, I need to know what is the top node in the stack. So I'm going to have a reference to the top node in the stack. Right? And now I need to make the node class. Right? So at this point, you get to choose where do you want to create your node class. Right? You can make it its own separate class if you want to. Right? Alternatively, you can also make it a member class. Sorry, there's something missing here. You can make it a member of the linked stack class itself. Right? There's actually there's a typo here. Right? So I'm going to make it a private static class. Right? So there's our node class right there. So ignore this private static business for the moment. Right? And just look at the node class itself. Right? So node is a class that's defined inside of the linked stack class itself. What's inside of a node? Well, every node has a reference to a string, that is the element stored in the node. Right? Every node has a reference to the next node in the sequence. Right? And that's all we really need for this particular class. Right? We just need to keep two pieces of information. It's convenient to make a constructor. Right? So our constructor takes in an element and the next node in the sequence and simply sets this elem to elem, and it sets this next to the next node in the sequence. Right? If you want to make a node that doesn't have a next node in the sequence, you just pass in null for next. Right? And away you go. Right? So there's an example of a nested class, right? And we saw an example of a nested class, I think 2 lectures ago, when we first started talking about interfaces. Right? The difference here is that node is a static nested class. Yeah, right there. It's a static nested class. Okay, so what is a static nested class? So a static nested class is the simplest kind of nested class that you can have in Java, right? So it's compared to the previous nested class I showed you, which was an inner class. Static nested classes are simpler. So all it is, it's just a regular class that happens to be defined inside of another class, right? That's it. There's no other difference between it and a regular class. Right? It's called a member class because it happens to be inside of another class, right? And it belongs to the class that it's in, right? So our node class belongs to the linked stack class, right? And so what does that mean as far as linked stack is concerned? It means that linked stack can see everything that's inside of a node, right? So it can see all the private stuff that's in a node because the node class belongs to linked stack. So the class that the member class is in gets access to all of the features of the member class, right? Even the private features. What is the difference between a static nested class and an inner class? Right? So a static member class does not have access to the private members of the enclosing class. So in this case, a node doesn't know anything about a linked stack. Right? So node has no access to the private fields of linked stack, and it doesn't need it, as you'll see shortly. A static nested class is just like a regular class, right? So it's not the same as as an inner class, and so that means that instances of the nested class can exist without the enclosing class, right? So nodes can exist, right, without having a linked stack object anywhere. Okay, so you might wonder, so why did we bother creating this static nested class? And why is it private, right? And so the answer is that anybody outside of the linked, anybody who's just using the linked stack class, right, never needs access to a node, right? And they don't even care, and they probably don't care that your class is implemented using a linked sequence of nodes, right? So what does a user of a stack care about? Well, they care that there's a size method, they care that there's a push method, they care that there's a pop method, right? It's none of their business how the actual workings of the class are implemented, right? So they don't need to know that this node class even exists, right? By making the node class private, right, that makes the node class invisible outside of the linked stack class. If you had made it a regular top-level class, right, that class automatically becomes either public or package private. Right? There's no way to make that class, the node class, private if you define it in its own file as a top-level class. Right? And so that means anybody else can use the node class if they wanted to. Right? Okay, so I guess we just jump into Eclipse. So now that we've got our nodes, how do you go about implementing linked stack? Right? And it turns out it's quite easy, right? Once you wrap your head around the fact that these nodes are joined to one another, right? That's the only tricky part in implementing this class, right? So what does the constructor do? Right? Well, what does any constructor do? It initializes the fields of the class, right? So what are my fields? Well, there's size, and there's this thing called top, right? Which is a node, which is the top node. So in an empty stack, the size is 0. So that's easy. And in an empty stack, there is no top node. So that's also easy as well, right? We can set this top to null. Right? Again, remember, null means no object. How do you implement the size method? Well, we've got a field that represents the size of the stack, so we can just return this dot size. Right? So that's easy. So notice there's an override here, right? We're overriding the method from the interface here. Right? The interface says there has to be a size method, right? And so we need to provide a size method in our class. Right? We don't need isEmpty. Right? IsEmpty was a default method in the interface, so we don't have to implement it. We get it for free from the interface. So what about push? Right. So push is straightforward, right? So if you go back to the slide that describes the process of pushing a node on an element onto the stack, right? We want to make a new node to hold the element. Right? So how do you make a new node in Java? Well, you write new node, right? And we're going to store the element in the node, right? Set the link of the new node to point to the current top node. Sorry. Right. So our constructor lets us set the link for the newly created node so that it refers to another node, right? Up here in the constructor, right? So passing in this dot top causes the constructor to set n.next to be equal to this dot top. Right? So if you don't like that, you can write it like this as well, also. Right, so make your new node, right? The next link currently points at nothing. Right, now make the next link point at the current top node. Right. Okay, now step 3, set top to refer to the new node. So this top equals n, right? Step 4, increase the size of the stack by 1 because you just pushed an element onto the stack, right? So this size plus plus, and that's it. What about popping an element from the stack? So again, just go back to the slides. Oops, sorry, right there. Right, so to pop an element from the stack, we need to remember what is the element currently at the top of the stack. So remember, what is the element currently at the top of the stack? Well, the element currently at the top of the stack is just the element stored in the top node. Right? The element stored in the top node is just this .top.elem. Step 2. Right? Set top to refer to the next node deeper in the stack. Okay, so remember, how do I get to the next node that's deeper in the stack? Starting from the top. Right? Well, the top node has a field called next that refers to the next node in the stack, right? So that's the next node that's deeper in the stack. So set this top to this top.next, right? And that adjusts this top so that it now points at or refers to the second node in the stack. Right. Step 3, subtract 1 from the stack size. So this size minus minus. Right? And finally, step 4, return the element that was in the old top node, right? Which is that. So simply return popped, right? And of course, don't forget step 0, right? If the stack is empty, we should throw an exception because you can't pop an empty stack. Right? And that's it, right? There's your stack class using linked nodes. Okay. Any questions so far? All right. Iterating over a linked sequence. Okay, so our representation of the stack is just a sequence of nodes that are joined one to the next, right? And so that means that if you get a reference to a node, right, you can figure out what are all of the next nodes after that node. Right? There's no way to easily go backwards, right? So if you look at the picture here, right, notice that our arrows all point in this direction. So if you get a reference to the A, there's no good way to get back to the B, right? Similarly, if you get a reference to the B, there's no simple way to get back to the C, right? So we're always going in one direction. So if you get a reference to the top node, though, it is possible to get to every other element that's in the stack. Right? And so the way you do that is you start at a node and you just iterate over the nodes, so you follow the links until you get to the node that you're interested in. Right? And so whenever you're working with these linked structures, iterating over the sequence of nodes turns out to be a very common operation. Right? And so you know that you're done iterating over the nodes when you find a node whose next link is null. Right? So remember, that's how we indicate the end of the sequence. Right? So starting at the first node of the sequence, all you do is you follow the next link to get to the next node until you reach the null node. Right? So in general, you want to iterate over a sequence of nodes, starting at some node. So here, starting node is your node that you want to start at. Right? All you do is you write a little while loop. Right? So while n is not null, right, you do something with the node here. Right? So maybe look at its element or do something with it. Right? And then advance to the next node. Right? So that you can process the next node in the sequence. How do you go to the next node? You just do n equals n dot next. Right? N next is the next node in the sequence. Right? If I make n, if I assign that reference to n, right, that makes n refer to the next node in the sequence. Right? When you're done with the loop, right, this condition is false, so you know that n must be equal to null. Right? So whatever you do down here, don't use n, right, because n is null. Right? So you can reassign n to something else, right, but don't try to do anything with n here because there is no node at this point anymore. Right? And so there's your general iteration pattern, which is worth remembering. Right? So if you want, so this is a picture of what's happening. So I'm going to start at the top of the stack. Right? So n here is just this top. Right? Is n null? The answer is no. So we're going to do something with this node. Right? When I'm done processing this node, I'm going to follow that link there, which is n next. Right? So n equals n next goes to the next node. Right? Is n null? The answer is no. I'm going to process this node, so I'm going to do something with the element. When I'm done, I'm going to follow the next link. Right? So n equals n dot next to get to here. Is n null? The answer is no. Process the node, follow the next link. Right? So n is now null. So now the loop stops. Right? And that's it. Right? So if you want to generate the string representation of a stack, right, all you want to do is you want to iterate over the sequence of nodes. Right? Probably getting the string representation of each element as you go. So I'm going to use a string builder to help us out here. String builder is just the mutable version of string. Right? So it behaves similarly to string, except that you can actually change the string that the string builder represents. Right? So I'm going to start with the string stack, starting at the top node. Right? Every time I find a node that has something in it, right, so it's not null, I'm going to append a new line character to the end of the string. \n is the new line character in Java and many other programming languages. Right? So I'm going to append a new line. I'm going to append the new line character to the end of stack. Right? Then I'm going to append the string representation of the element. Right? So remember, m.elem in our case is just a string. Right? So that's going to be whatever the element is as a string. Right? And then I'm going to go to the next node in the sequence. Right? If there's another node in the sequence, I'm going to stick a new line character onto the end of the string, right? And then append the element to the end of the string. And so on and so on and so forth. When I'm done processing all the nodes, I'm just going to return the string representation of the string builder. Right there. So there's the code for it right there. Right? So if you run the little main method that's here, right, we make a new link stack object, and then we push A, B, and C on top of the stack. Right? And so we can then print out the stack, the size of the stack, and then the stack itself. So when you do that, you see that the stack size is 3, and the string that you get is the string stack, followed by the stack drawn from top to bottom in a vertical line. Right? I'm then going to pop the stack, right? Print out the popped element, its size, and the stack itself. Right? So after popping the stack, right, the C comes off the top. Right? You now have a stack of size 2, and your stack now looks like that. right? And if you keep on going, eventually you end up with the empty stack down here, right? And the empty stack is just the word stack followed by a blank line. Oh, I guess as long as we're here, we might as well go back to Eclipse. Okay, so now that I've shown you how to iterate over a sequence of nodes, we can now do something. We now do something else in the class. Okay, there's our no argument constructor. It might be useful to provide a copy constructor for this class as well. Right. So in other words, you might want to provide a constructor that copies another linked stack. Okay, and so the question is how do you copy another stack? So remember, the thing to remember here is that when you make a copy of the other stack, right, you want your two stacks to be independent of one another. Right? So in other words, if you push an element onto your copied stack, right, that does not push an element onto the original stack, and vice versa. Right? If you pop an element off the original stack, right, the element does not get popped off the copied stack. Right? So you might, at this point in the course, say that, well, I know how to copy something. Right? I just copy its fields. So you might want to write the following. Right? So if I make a copy of the other stack, I know that the stack sizes, they must be the same, right? And then I need to also copy the other stack's top node, right? And this doesn't work, right? Right? So in Java, you have to remember what it means when you write that piece of code, right? This top equals other top. So remember, top is a reference to a node. Right? And so you're saying the top node of this stack is the exact same node as the top node of the other stack, right? Which is not what you want, right? So now both stacks are sharing the same sequence of nodes, right? If you manipulate one stack, the other stack changes. That's not what you want, right? What you want to do is you want to copy the other stack's sequence of nodes, right? So don't do the following. Right, so that's wrong. So what do we need to do instead? Right, you actually right, so you actually need to make a copy of the other sequences set of nodes. Okay, so to copy the other sequences set of nodes, you have to iterate over the other sequences set of nodes. Right. Right, and I'm going to leave that as an exercise for the student here. Right. So you're going to write a little loop, right, that iterates over the other sequence of nodes. As you iterate over the other sequence of nodes, you're going to copy those nodes, right? And you're going to, and you have to make sure that you reassign or set the top node of your copied stack to refer to the new top node that you copied from the other stack. Right? So at some point in time, you should attempt to implement that copy constructor there. All right. There's something funny about the node class. Right? The thing that's funny about the node class is that you have an object that has a reference to an object of the exact same type. Right? So every node has a reference to a node. Right? That node has a reference to another node. Right? And that reference might have a reference to another node, and so on and so on and so on. Right? Eventually, one of those references is null. Right? So the sequence ends at some point. And so this means means that node is an example of structural recursion. Because every node refers to another node, right? You can imagine that any node is just the top of some other stack. So what do I mean by that? Right? So in this picture here, right, I know that C is the top of the stack CBA. But if you consider the node that has the B in it, right, you can imagine that's a stack of size 2, right? It's the stack containing the B and the A. Right? And similarly, if you look at just the A, right, that's the stack that consists of just the A. Right? So every node, as you go deeper into the stack, right, you can imagine is the top node of a smaller stack. Right? And so if you think about that for a second, that looks a lot like a recursive algorithm. Right? And so the recursive structure of this class node makes it quote unquote easy to write recursive algorithms that operate on nodes. Right? So toString is an example of a method that you could write recursively instead. So to write toString recursively, I'm going to create a separate method that does the actual recursion. Right? So the method that's actually recursive is called toStringHelper. Right? And its input is a node n, which you can imagine is a top node of some stack. Right? So toStringHelper generates the string representation of the node, of the stack having that top node. Okay, so if someone passes in null, right, what does that mean? It means the stack is empty, right? And so the string representation of the empty stack is just the empty string. Right? If someone passes in a node that's not null, right, then the string representation of that stack is just going to be the element that's in the node, right, plus the string representation of the rest of the stack. Right? So to get the string representation of the node n, it's just n.elem, right? The element that's in the node, right? To get the string representation of the rest of the stack, right, you need to pass in, you're going to recursively call toStringHelper, passing in a node, passing in a reference to a node that is the top of the rest of the stack, right? That's just n_next. So here we can recursively call toStringHelper passing in n_next. Right? We want our elements to be on their own lines, so that's why there's this the new line character at the front of the string. Right? Eventually, right, toStringHelper will result in n_next being null, right? Because every time you're calling toStringHelper, you're going to the next node in the sequence. Eventually, you get to the bottom node. When you're in the bottom node, n.next will be null. So you'll call toStringHelper with null. That'll return the empty string, and then the recursive, and then that will cause toStringHelper to return back to toString. Right? And so the toString method prints out the word, starts with the string stack, and then just generates the string representation of the rest of the stack starting at the top node. Right? And so there's an example of of using a recursive method exploiting the recursive structure of the node class itself. Right? So in SYS 235, probably, you're going to see a lot more of this stuff when you work with binary trees and graphs. All right, any questions about, I guess, implementing a stack with a linked sequence of nodes? Anybody? Anybody? All right, I think we'll call it quits there for today. And we're going to start to look at some other data structures in the coming weeks.